So, last class I have solved 3 examples to calculate immediate as well as consolidation settlement and also bearing capacity. One more example I want to solve for particularly consolidated clays, as we have discussed earlier during your settlement analysis. There is a footing, here it is footing 1 meter, then here it is 1.5 meter, there is a water table here, then pressure intensity on the footing is 150 kilonewton per meter square. Then sand gamma is equal to 16.5 kilonewton per meter cube, and here it is 0.5. Gamma saturated is 17.5 kilonewton per meter cube, and there is a soft clay, normally consolidated clay. NC means normally consolidated clay. This depth is your 2.5 meter, and these properties are given. Cc is equal to 0.32, Cs is equal to 0.09, gamma is equal to 16 kilonewton per meter cube, Es is 6000 kilonewton per meter square, mu is equal to 0.5, E0 is equal to 0.8. So, find it out the consolidation settlements. So, in this case, to find it out the consolidation settlement, generally we have to calculate delta P average, which is equal to 1/6 of delta P at top plus 4 times delta P at middle plus increase in stress delta P at bottom. This is what your consolidation settlement to do it. Then for this, find it out P0. P0 up to your 1.5 means up to this layer or at the middle, that means this will be 1.25 meter. So, your P0 is equal to 2.5, 1.51, 2.5 into gamma is 16.5 plus 0.5, 0.5 into 17.5 minus 9.81 plus 1.25, your gamma saturated is your 16, which is equal to 16 minus 9.81, it comes out to be 52.84 kilonewton per meter square. Now make it a tabular form. This is your M is equal to L by Z. This is your Z. Then this is your N is equal to L by Z. Then this is your influence factor, and this is your delta P is equal to Q0 into I. Size of the footing is given 1 meter by 2 meter. Now the footing size is 1 meter by 2 meter, means this is 1 meter, and this is your 2 meter. Now increase in stress, once you are going to find it out, this is a rectangular loaded area and at the center you have to find it out. So basically you have to make by M and N and Z what depth you want to find it out, and based on that, because 3 Z, one is your at the top, what is the Z, at the middle and at the bottom, top, middle and at the bottom. So M is equal to L by Z. So Z is your L by Z. If I take it, Z, what is the distance? If you look at here, Z, it is your 1.5 plus 0.5. So then it is your 2. 2 by 2 is your 2. L by Z is your 2. So M is equal to 2, 2, 2. Z is equal to, at the top up to here it will be 2. Then here it will be your 2 plus 2.5 by 2 at the middle, up to here 1.5 plus 0.5 2. Here it is your 2.5 by 2, which is equal to 3.25, and here it will be again 2 plus 2.5 at the bottom, 2 plus 2.5, it will be your 4.5. M and N, you can calculate also N. Then I comes out to be, I is your 0.190, which is equal to 0.085, which is equal to again 0.045. Sorry, M will be also varying, N also will be varying. M will be for depth L by Z. If L is equal to, if B is equal to 1 meter, say L is equal to 2 meter, M is equal to L by Z. L by Z means L is equal to 2 by 2, 2 by 2, which is equal to 1. Here it is your L by Z, L is equal to 2 by 3.25. Here it is your 2 by 4.5, and N is equal to not L by Z, this is your B by Z. B by Z is your, how much is your B? B by Z, B is equal to 1, 1 by 2, 1 by 3.25. Then here it will be your 1 by 4.5. This is what you are supposed to calculate it. This way you can calculate, there are chart at the middle, or you can do it, make into 4 equal parts, 1, 2, 3 and 4. Here it is 1 meter, 1 meter, here it is your 0.5 meter, 0.5 meter, then sum it up. Then delta P is equal to Q0I, it comes out to be 28.5, 12.75, 6.75. Now calculate is your delta P average. Delta P average is equal to 1/6 28.5 plus 4 into 12.75 plus 6.75. 6.75 is your at the bottom increase in stress, 12.75 is your middle, 28.5 is your top, and 1/6. It comes out to be 14.38 kilonewton per meter square. You can check the calculations. I have done it. You can use your calculators and check this whether these factors are I is correct or not. This is the procedure. There might be small mistakes. So consolidation settlement is equal to Cc by 1 plus E0 H log 10 P0 plus delta P by P0, which is equal to Cc by 1 plus E0. Cc is equal to 0.32 by 1.8 because E0 is 0.8 into H. H is your 2.5 at the middle, and log 10 52.84 P0 plus 14.38 divided by 52.84, which comes out to be 46.5 mm. So this example why I have solved, in many times you will be asked, maybe in an examination you will be asked to find it out the consolidation settlement of a normally consolidated clay where the footing is any shape, it may be a square, it may be a rectangular, it may be circular. So basically you have to find it out P0. If it is a normally consolidated clay, delta P average is 1/6 of this. Then based on the M and N you find it out I and Z, then find it out your delta P, then from there you calculate your delta P average, then find it out consolidation settlement Cc by 1 plus E0 H log 10 P0 plus delta P by P0. H is your 2.5 meter total height and Cc is your 0.32 and E0 is 0.8 and it is 1.8 log 10 P0 plus delta P by P0. So it is coming out to be 46.5 mm. I think this is the last example and we will give, maybe in latter part I will solve many more examples once this design of this foundation completed, then I can solve many more examples. So typical examples I solve it, earlier also I have solved few examples, how to consider the pressure bulb, what depth you are going to consider, how to calculate your bearing capacity. So let us start the next one, that is primarily most important one, means almost all part I have covered. If you look at here, I cover your site investigation, method of drilling, sampling, in situ test, SPT, CPT, plate load test, dynamic test, groundwater level, bearing capacity, general, local and punching shear failures, corrections for size, shape, depth, water table, compressibility, ultimate and allowable stress, method based on your in situ test. Also I have finished settlement of foundations, that means for sand, for clay, again for clay immediate as well as consolidation settlement. For clay, what are the different methods, stress path method also I have covered. Then stresses in soil, and last few class I was covering, that is by means of your Bosenick's theory, by point load, then strip load, then rectangular loaded, then circular load, then approximate method, then equivalent point load methods. Up to this I have covered. Then I solve few examples Now, let us start with this design of the foundations. So, type of the foundations also earlier I have covered, that means your shallow, deep, isolated, combined, mat. This I have given a brief introductions what are the different types of these foundations. If I can show you, just giving a very brief one, how far I have gone through it. You can just see it. Yeah. This is what I have covered in the beginning part. Foundations, shallow and deep, and shallow is classified, because I am repeating, because I am going to start now design of these foundations. Foundation two types broadly, one is your shallow and deep. Shallow foundations, again footing and raft. Footing again isolated, combined and strip. Raft is conventional raft and buoyancy raft. Deep foundation again two, one is pile, other is your caisson or well. Then there are also machine foundations, retaining structures, gravity retaining wall, cantilever retaining walls, counterfort retaining walls, as well as reinforced earth walls, RE walls. This is called reinforced earth walls. So, then I explained isolated footing where the case and to support your column loads, and combined footings and strip footings. Then also I have gone to your raft or mat foundations. Large number of columns are there, in that case one single slab is required, raft and mat foundations. Then I have covered your different raft, conventional raft and buoyancy raft, then pile foundations, piers and caissons. Then shallow foundations, the definitions also I have started. If dF by B is as per your Terzaghi less than equal to 1, we can say shallow foundation, but it has been modified. If dF by B staying between 2 to 3, then this comes out to be a shallow foundations. Now, if I with these descriptions, let me go to the next part, that is your design of foundations. Design of foundations. Design of foundations. In design of foundations, design of foundation, let me start with the first one, that is your shallow foundations. I have covered the basic parts. So, now I will go slightly faster, so that I can cover the syllabus. And in the shallow foundation, let us start with shallow foundation in sand. Start with first one is your shallow foundation in sand. What is the bearing capacity? Bearing capacity is CNC plus gamma DF NQ plus 0.5 gamma B N gamma. Because in sand C is not there, let it be 0, then it will be your, I am just rewriting half instead of 0.5, half gamma B N gamma plus gamma DF NQ. So, net ultimate bearing capacity will be half gamma B N gamma plus gamma NQ minus 1 df by B putting it into B. I am taking out the B outside, the net ultimate bearing capacity. So, this is my first term and this is the second term. So, if you look at here, so second term is a function of df by B. So, now net safe bearing capacity Q safe net, which is equal to gamma n gamma by 2 plus NQ minus 1 into gamma df by B divided by your factor of safety into this is your B. So, net safe capacity also we called safe bearing pressure considering bearing capacity. Safe, look at what the write up I am putting it, safe bearing pressure considering bearing capacity. It is called SBP, safe bearing pressure SBP considering bearing capacity. Now, if I plot it, how it looks like? SBF versus B kilonewton per meter square, and how it looks like, say for example, say df by B you take it 1.0, gamma is equal to 16 kilonewton per meter cube and factor of safety is equal to 2.5. Now, it is varying from 0 to 1.0 and here it is varying from 0 to 600. Now, if you look at here, let me put it very 1, then 2, 3. Now, let us say this is 0.4, then 0.8, then 1.0. So, here is equal to n is equal to 5, here n is equal to 40, here n is equal to 50, and this is your B in meter. How it looks? Look at the graph. So, safe bearing pressure considering bearing capacity, particularly it is if all other terms are constant, gamma is constant, n gamma is constant, phi is constant, NQ is constant, then what will happen? SBP is directly proportional to B. It is directly proportional to B. Then what will happen if it is directly proportional to B? That means it will increase linearly with increasing. So, there is a ratio B, means you cannot increase, earlier also I said you cannot increase the B up to infinity. Do not think that if B has been increased up to infinity, then it will increase infinity. It has been seen up to certain B it is increased, then there is no effect of the width of the foundations, then it remains constant bearing capacity for different n values. So, starting from n is equal to 5, 40 and 50. So, if I join it in this way, fine, this is n is equal to 5, 40 and 50. Now, this is a case 1, this is considering only safe bearing pressure, that to bearing capacity. Now, come to second part of this and soil pressure for settlement. There are two while calculating the capacity, one is considering bearing capacity, other is considering settlement. Soil pressure for settlement थोड़ा बंद करो तो. Let us take it soil pressure for settlement. As per code, BS code, elastic, it is based on your SPTN value, which is equal to 0.722 P by n minus 3 into 2B by B plus 0.3 whole square. P is equal to intensity of applied pressure which is equal to kilonewton per meter square. Generally some books they say P, some books say Q, it does not matter, it is up to this, because why the Q I have not taken, Q generally it is your bearing capacity, that is what I avoid this Q. Then B is equal to width of footing in meter. Say for example, say let us say settlement is equal to 1 mm. So, then soil pressure from this equation you can calculate P is equal to 1.385 n minus 3 into B plus 0.3 by 2B whole square. So, P is your soil pressure, there are two P, one is your small p, one is your small p, another is your capital P. This is soil pressure, sorry, this is same I am sorry. So, intensity of applied pressure P. So, this generally termed as soil pressure for settlement. Settlement, it is called SPS, earlier SBP, soil bearing pressure considering bearing capacity, soil pressure considering settlement, it is SPS. Let us plot look at this SPS kilonewton per meter square, how it is varying. It is for typically n is equal to 30 and settlement is equal to 50 mm. B is equal to in meter, it is 0 to 10 meter. So, what is the conclusion I can draw from this? one is your SBP, soil bearing pressure considering bearing capacity, one is your soil pressure considering settlement. That means SBP increases linearly with B, then soil pressure settlement decreases hyperbolically with B. So, one is your SBP increase linearly with B, SPS increases here, decreases hyperbolically with B. Let me superimpose how it looks like both these. Allowable soil pressure, out of these two whichever is minimum, that is your allowable soil pressure. Allowable soil pressure, that is your ASP term, kilonewton per meter square, and this is your B varying from 0 to 1. Let us say one case I am putting it in this way. This is your say SBP. Of course, SBP increases linearly for a particular value of B. Beyond that, there is no further change in bearing capacity even if you increase the width of the footing. And let me take it in this way. Case 1, case 2. So, in this case what has been taken? Gamma is equal to 10 kilonewton per meter square for plotting this graph. dF by B is equal to 0.5, factor of safety is equal to 2.5, gamma is equal to 16 and N is equal to 30. So, this is for considering settlement of 25 mm. 25 mm is as per our IS code requirement, that is your permissible settlement for normal building. For other buildings, multi-stories, permissible settlement is your S is equal to 50 mm, sorry, rho is equal to 50 mm. Generally what will happen if I draw a authenticate here? Let me put it in such a way that it will be very, if you understand this, then later there will not be any problem. So, this is your B, and this is your B prime, and this is 1 say, and this is say suppose 2, then 3, then this is your 10. So, after certain part, as we have seen here, after certain part it remains constant, certain width. If you look at here, also your soil pressure for settlement, it decreases hyperbolically with B. Now, if I draw it a common form in this way, here I am drawing also in this way. That means this is your 10.5 into N, this is your 21 N. Generalize it, because soil bearing pressure increases linearly with your B, and after certain B this will remain constant. Suppose say 0.4 meter, suppose in this case 0.4 meter, even if you increase the B, there is not increase linearly, rather it will be constant. So, that case has been put it here and here it has been put it. For generalizing, it has been drawn with both the graphs has been put it. For considering residential building of settlement of 25 mm and other is your 50 mm, generally allowable soil pressure has been taken. If I put it in a very flat way, this is your 10.5 N, this is your 21 N. This is a kind of thumb rule in design. So, considering both SBP, soil bearing pressure, as well as soil pressure considering settlement, out of these two minimum is your allowable soil pressure, that comes out to be your 10.5 N and 21 N. 10.5 N for your settlement of 25 mm and 21 N for your settlement of 50 mm. This is what this sand we have derived for particularly shallow foundations. On in sand we will go shallow foundation in clay, then mat, raft, all will go step by step. Now, what is the codal provision for water table corrections? I have explained also earlier, but once again writing it for your, you can just note it down. This is your B and this depth is your B. This have been explained. This is your surcharge zone, this is your wedge zone, and this is your DF, depth of foundation, and this is your DW. So, if say CW is equal to correction factor for water table then it will be 0.5 plus 0.5 dW by dF plus P. This correction factor will be added, means multiplied. So, if dW is greater than equal to dF plus B, then correction factor is equal to 1. If dW is less than 0, then correction factor is equal to 0.5. Generally it varies between 0.5 to 1. This earlier also I have discussed, there is nothing new. So, water table correction has to be added. Another most important part, try to understand another most important part. So, this is required for designs because for sand it is based on your SPTN, nothing else. Now, we draw a conclusion for settlement of 25 mm, for settlement of 50 mm, allowable soil pressure is based on your SPTN, that is your 10.5 N and 21 N. Now, draw this N versus your depth. N versus your depth. Why we take cumulative average? One is your whatever you are getting N from your SPT after corrections, another is your N cumulative average. So, it is 0, 1, 2, 3, 4, 5. Generally it goes this way, whatever the way. Then cumulative average also plot it in this way. Why cumulative average? Why we are looking for this cumulative average? Since I am just writing out, you can note it down. Since all effective overburden pressure are less than the standard value of hundred kilonewton per meter square, then this is benchmark for BS code. It is seen that corrected N values are higher than the values recorded in field. Since N value recorded at an interval, generally N value how you have recorded at an interval of 1 or 1.5 meter. So, variation of cumulative average, plot of N cumulative average with depth so very easily intermediate values could be taken from plot rather than interpolated by calculations. Basically, plot of the N cumulative average, another one, number 1, number 2, it reveals the relative picture of N values. At various depth. Are you getting? Do you understand what I want to say? All the effective overburden pressures, almost in residential means all, are less than the standard value of 100 kilonewton per meter square. It is means I am not saying that all are less, because depending upon the depth and how the effective part is coming, but in normal, in general, effective overburden pressures are less than your standard value of 100 kilonewton per meter square. So, it has been observed corrected N values are higher than the value recorded in the field. Whatever the value you have recorded, because it is less than your 100, corrected N values are always higher. Generally what will happen, how do you measure the N? N we SPT N, as I discussed earlier, every 1.5 or 1 meter interval below the ground surface we measure. Now, what advantage we are supposed to get from your n cumulative average? What advantage we should get it? First one is your, instead of, suppose here it is say 1 meter is your 0, suppose 2 meter some value, suppose 2 meter some value say 18, 3 meter some value say 20, and 4 meter some value say 22, here it is 21. As we observe from the field. So, what will happen if somebody wanted to find it out between 1 to 2, 1 is your 0, 2 is your 18, suppose 2 to 3, 2 is your 18, 3 is your 20, in this case you have to interpolate depth wise, which is not true. While taking the n cumulative average, intermediate values can be taken very easily because it is a cumulative average rather than interpolations. So, again it reflects relative picture of your n values at various depths. Look at n cumulative average how it is varying, here how it is varying. That is why for design purpose, in particularly sand, if n is given, n cumulative average has to be calculated. I do not know how far I can complete this example because this will take time. Let me start with this. There is an example, let us start with the design. Just I am writing this whatever is there. There is a building, in building there are, one is your interior column, other one is your exterior, then there is also, this is called exterior wall, and this is interior column, there is outer column. Interior column load is given, my interior load is given, that is your 1.95 mn mega Newton considering dead load plus live load, and here it is given exterior wall, it is given 85 kilonewton per meter considering dead load plus live load, and there is a gap, this is generally used 0.15 meter of floor slab, right, and this is a sandy soil or sand, gamma is given 17.5 kilonewton per meter cube, and this is your below 2 meter, there is a water table, water is there. So, there is interior column, exterior wall, wall loading is there, interior column load is there, dead load, live load, dead load, live load, and there are depths where SPTN has been reported 0, 1, this is your 2, 3, 4, and at the end it is 5 meter below the ground surface. There are 2 boreholes, first one is your borehole 1 SPTN 1 is your 16, 2 is your 17, 3 is your 19, 4 is your 20, 5 is your 18, then second one is your borehole 2, that is your N2, this is your 15, this is your 18, this is 23 and this is 24 and this is your 20. This is what you are given. Design a suitable column footing in sand. There is a soil, sand is there, gamma is 17.5 kilonewton per meter cube, water table below 2 meter. There is one interior column, there is one exterior wall, load is given dead load plus live load. I will discuss next class dead load plus live load, what does it mean. Here it is dead load plus live load. These are all practicals. Then boreholes in that site, 2 boreholes have been made, SPTN value has been reported up to 5 meter. Design a suitable footing. So, I want to keep it here. Next class, because this will take complete more than one lecture. So, next class I will completely design step by step and I will finish it up. Thank you.